Lower. That's it. Let's bring it a little forward. More. It's pretty good. Turn off this blinds. Let me put the full screen for you. Alright, now you can just click. Make sure it's working. Try to click on it. Again? Again? There you go. It's working.
How come this is doing my
It does.
Alright, so my partner's not here, but I'll start. My section is 10.1.
Did you guys fill out
temperature, energy, and heat.
Did you fill out one of these?
Lugo.
Use the flower one of these. What? Where'd you fill it up? Kill your vibe. Guys, make sure you have both your partner's names in here and the thing. Remember that if you talk during somebody else's presentation, it comes off your presentation grade. You're welcome to raise hands and ask questions, all right? But if you have questions or if they're going too fast and things like that, you pass the buzzers around. However, you know, please abstain from interrupting or being disruptive during people's presentations. Okay.
Okay, so we're starting again. My name is Labardo Lugo Lopez, and this is Juan. Yeah. And our section is 10.1. Temperature. Temperature is proportionally the average kinetic energy in a substance. So our body temperature is about 9.6. Yeah, that's the average. So if you're like 103, that's not normal.
96, right? Not 9.6.
No, 98.6.
Oh, 9.6. Sorry, I didn't hear it right. Sorry. Forget.
So thermal energy is basically the energy that something has, like as in heat. But heat is actually like two different things. Thermal energy and heat are two different things, even though I think it's the same thing. Thermal energy is just something that, like if you were to measure something, like the temperature that it would have at that instant. It's the best explanation I can give.
Alright, thermal equilibrium is a system is in thermal equilibrium when its temperature is constant and there's no net thermal energy, or it has zero net thermal energy. So let's say, can I use this board?
Sure. Absolutely.
So you get a hot brick that if someone took notes, you should remember this. And you have lead. That's a cool brick. And we're going to do this. That's a hot brick. And this hot brick has, let's not say a number because I'm not HO students is going to go with the answer. Let's say this is hot. Right? And cool. Thermal equilibrium would be for both. Use the same temperature. Okay, thank you, Luke.
Alright, heat would be the temperature that you actually feel. It's the energy that's transferred from one object or body to another one. So let's say heat is what is basically happening. Like the heat from this from the hot plate is going to here. So that's basically what it is. Like thermal energy is just what it has, and then yeah.
There you go. I was waiting for you guys to say that. That was good. Make sure to clarify, you guys did good there. I was worried you were not going to do that, but that's a very important distinction. Thermal energy is what you have. So you can talk about how much thermal energy this has right now. That has to do with the internal movement of the molecules and stuff. But heat is how much energy is being transferred between two things. Does that make sense? So you cannot have heat, right? Heat only exists in the sense of what? Transfer. Does that make sense?
If they have the same exact temperature, they're not gonna transfer anything. They have to have different temperatures. So one has to be hotter or colder than the other.
That's a zero flow, I think. That's what I'm talking about.
Absolute zero is the lowest temperature that you could possibly achieve, which is negative 273.15 degrees Celsius.
What does that mean?
What do you mean? How how would you want me to?
How would you rank absolute zero in terms of thermal energy?
Thermal energy?
How much thermal energy does something at absolute zero have?
For renewable energy.
None. Exactly.
No kinetic energy, no potential.
Right. So that basically means that you have no heat to give. Does that make sense? All right.
So if you get Celsius, I'll go
Sure.
to the next one. I'll do it for the next one.
Celsius is based on the freezing point and the boiling point of water. So the freezing point of water would be 0 degrees Celsius, while the boiling point.
Can you guys write that up? I'll give you a marker. This is important, guys. Got to have, guys. Remember, unfortunately, we don't have topics on this, but this is actually important stuff. We're supposed to learn this stuff in the camp, some of this, right? But because it's not going to be in the video tour over there. So I'd rather you guys learn the white space.
I have zero.
That's cool.
The freezing point of water and the Celsius scale would be 0 degrees Celsius. And then the boiling point of water would be 100. So it'd be it's basically just based on the boiling point and freezing point of water, and that's basically it.
Okay. Everybody should know that. Okay, next one.
Fahrenheit is what we use to measure here in the United States. This is more worldly. More other countries use this, but the United States we prefer Fahrenheit, which the boiling point for that is 212 degrees Fahrenheit, and 32 degrees for freezing point. Since we're gonna do that there. We're gonna move on to Kelvin.
In Kelvin, absolute zero is just the Kelvin. In the Kelvin scale, absolute zero is 0. So, like he said, like Lombardo said before, the Kelvin scale and the Celsius scale. The Kelvin scale, it would be 0 Kelvin equals negative 273.1 Celsius.
So if I want to convert from one to the other, I just add.
You just add.
Also, or yeah, add that much.
Celsius, not to Fahrenheit.
Okay.
So for Fahrenheit, it would be something else, but I don't quite remember right now.
It's okay. Who are these people?
Okay, Anders Celsius. The Celsius is named after him. He's a Swedish astronomer. He was born in 1701 to he died 1744. Okay, he came up with the system of the Celsius, which is easier to measure because you can think of freezing point at 0 and boiling point at 100. I'm going to show you. Now I'm going to show you how to convert from Celsius. From Celsius to Fahrenheit, which is, I believe, 9/5 times Celsius minus 32 equals Fahrenheit. Okay.
All right, and Gabriel Fahrenheit was the creator of the Fahrenheit scale. He was born in 1638 or 1638 to 1748, I think. 1748, somewhere around there. I know this individual. That's basically it. And here, you can show that the heat of the water goes overnight, like at 20 something degrees Fahrenheit, negative 100 degrees something degrees Fahrenheit, and what happens is the heat from the outside is telling you that the y-axis on
The boil is the water boil is the dry ice.
right, this is what happens. And then here, I don't know if you let's do this.
Is it sure? We can go outside and look at it. Yeah, sure. So you're supposed to go outside for this?
Wait,
All right, let's go.
here are your test
I know
questions.
Oh, by the way, So here's the thing. I'm going to post, remember these things on a presentation folder for thermodynamics. If you go to Unit Files, thermodynamics, his presentation is going to be there. Is that clear? Now, if you answer the questions, all right, by Friday, right? So, I know I don't have you on Friday, but if you come by on Friday and give me the questions answered, all right, you can get points for that as well at the normal HLQ ratio, which would be 25 points per set. So it's an opportunity for you guys to cover those of you who have a lot of points missing.
So we get 25 per section.
25 points per person. You guys have to grade it. Understand what I'm saying? For all the people who turn it in. All right? Now, here's how it's going to work. You're not going to get the points now, obviously, because you have to turn it in by Friday. And then when we come back, I'll give it back to you guys. So it's going to be a while until you can see those points. You know what I'm saying? But you can do these points, turn it in by Friday, and you get it by answering people's questions. Is that clear?
Yeah, I got my picture.
Now, remember, the presentations are posted online. That's why you have to have the question in the presentation, so that people can see it.
I got my multimedia.
Sure.
This is equilibrium.
Can we click on it?
You're gonna have to copy and paste because I couldn't get a header so.
Is that on your lesson plan?
Yeah.
Okay, so we can do that.
Do from 1 minute and 30 seconds to 3 minutes.
Okay.
Well, we set up the demo.
All right, perfect. 1 minute and 30 seconds?
Yeah, so 3 minutes.
Just wait for the ad to skip. All right.
Momentum is conserved, they all eventually have the same temperature over time as those collisions start to equalize. So if we look at a simulation of that, I'm going to take an iron object and I'm going to put it on a brick object, and we can see that the temperatures don't change. And the reason why is they have the same temperature. Now let me heat up the iron, so I'm giving it a higher amount of kinetic energy. The molecules are moving around. We can measure that by using a thermometer. Now what happens as I put it on the brick? You can see it's lowering the temperature, but where is that energy going? It's going to the brick itself. What happens after time? Eventually, we've done it right now, we've achieved thermal equilibrium. They're going to be the same temperature. I could do the same thing with the water. So I'm going to heat up the iron. I'm adding more energy to those molecules. They have a higher amount of momentum. What happens when I throw it into the water? You can see there's a decrease in the temperature of the iron, increase in temperature of the water. Eventually, due to conservation of momentum, they're the same. What happens if I cool it down? So now I'm removing energy from that. It's actually going into the ice itself. What happens? Now I see a decrease in the water, increase in the iron, and so it's easy to figure out where that thermal energy is going. It's always going from the higher object or the hotter object to the colder object. Now this is macroscopically looking at it. What happens microscopically? Well, if you look at it, let's say we have these two objects, the one on the left and the one on the right. Which one has a higher temperature? Well, it's going to be the one on the left. You can see the molecules are going faster, they have higher kinetic energy. But watch what happens, and it'll be really subtle, but I'm going to connect these two together. The one on the left, remember, is going to have higher molecule speed than the ones on the right. And so if we watch what happens when they're connected, you can see they're colliding along that margin. And as they're colliding along the margin, they're transferring some of that momentum. What happens eventually, they end up at the same molecular motion or the same temperature. And did you learn to construct an explanation for what's going on as we achieve thermal equilibrium, not only at the macroscopic...
Alright. Do you see what the fuck you mean? I'm sorry this is recording. Who watches these things? That's the problem. Alright? That's part of your homework. This is excellent. Do you understand what I'm saying? And this is part of your homework. Alright? It's been there all year. I'm glad you showed this. Alright? Alright? No, I'm serious. Like, seriously. Like, your homework is to not do notes the day before they're due. Your homework is to do notes a long time before they're due, and then watch Bozeman. Watch Flipped Physics. Go to the Physics Classroom website. Play with it so you can learn more physics. And in fact, that little animation that he was playing with, the little thing, that's a FET. So you can play with those two and understand physics better. And now you have the gizmos to do it too. If you're not doing that, you're depriving yourself of the real homework you're supposed to have. And you learn nice physics because of it. Alright? That is homework, people. Watch Bozeman. All his videos for every topic is in the podcast folder for every topic. So you have three things. You have to take notes. Alright? Should we be going outside already? Or?
No, yeah.
Alright. You have to take notes. Alright? You have to watch videos. And then you have to clear this classroom. If you don't do that homework, you miss out on these things. Bozeman's excellent. All right? You want to say something about him?
Presentation.
Huh?
Go back to the presentation.
Sure.
Oh, man, go back.
Okay.
All right, let's go outside, guys.
Come on, hurry up, hurry up.
Yeah, take your time, guys. Let's go.
Quick one.
The president, you're roll up. Roll up, goddamn. Who's gonna go get that bottle? Not me.
Juan. Juan. I found one in the trash.
No, I just need this water.
Just pour one.
No, we got that. I need scissors.
Therese, where's scissors?
Quick, give me. Here, come on. Right here. Hold. Hold that, please. Fuck. No, it's actually. No, don't smash it. Don't smash it.
Not enough pressure.
Yeah, but we're gonna have to do something.
All right, hurry up.
I don't think we're running.
Okay, we do it right here. Step back into the lane. Quick, step back. Right here, step back. Step back that way.
Guys, I'm inside. That's freaking awesome.
As soon as I close this, it started getting hot. I was like, oh. Not today. I love mama.
That just gave me an idea. I have an idea. Get inside. Get inside. No. Hey, I have an idea. Get inside. Get inside. Come on. Hey, we're still doing the egg drop. Okay? But at the end of, like a couple months after the egg drop, I'll give you plenty of time to research and plan. Okay? Remember, guys, you're not supposed to be cheating and designing and copying things from online. You're supposed to think about it, come up with something yourself. And then I will be checking on the day of the egg drop online to see if your design was completely just cheated from someone else's design. Come up with something. Don't look it up. We're going to do whoever builds the rocket that goes off tallest, furthest up. Now, you can do whatever you want. You could have made a rocket out of this. Because if you put the bottle upside down inside of that cone, right? When as it explodes, it should shoot it up.
Actually, depends.
You could do it off your makeshift gunpowder. You could do it. You could do it off, stuff that use the pyrotechnics, right? Fireworks. I'll do it before you do something like this. You could do an air pressure rocket, right? You could do an air pressure rocket. Whichever way you do, we're going to do that. But don't worry about that for now. You're still working on your egg drop thing.
Guys,
Oh.
the end production by Thermal Boys.
Are you trying to say you're hot? Well,
Read that.
here's the grade. Your grade,
Read
it was
that.
an absolute 0. I'm kidding, man. I'm kidding. It was excellent. The only thing you guys didn't have is the report, the notes to give to students. You never gave me that. Make sure you give it to me, okay? All right?
Read that.
That's awesome.
Hey, keep this. If you,
All right, next 10.2. Let's get up here.
hey, Mom, if you want to keep this, so we can try doing the and again, but with more dry acid.
Okay, put it in there. Okay.
We did that yesterday. We did it with a small bottle at my house yesterday, but it was actually popped. But it was so loud that actually hurt our
We
ears.
can try it again. We can heat up the water a lot, make it really hot,
I
and
think it's
then.
because of the bottle. The type of bottle was too.
No, I waited way too long to close it.
Because the type of bottle was stretchy.
I go 10.2. Why you're not up here yet? Let's go.
Mr. Limo, we should have known we didn't physics being an antibio, the gummy bear thing.
Oh, that's a thermodynamics. I should do it. I should do it. I can still do it. All right. Let me just open your presentation really quick.
Wait, were we supposed to have a presentation?
We're supposed to have something I can share with the rest of the class, yes. All right.
We have a lead.
We'll see. Because they need to be able to have your questions. So if you have your lesson plan at least,
I just sent you the questions like separate.
but yes, they're supposed to be,
Probably in your box and phone. Me. I always right?
You guys send it to me?
Yeah.
So it should be here somewhere. Let's find out. 10 guys, take notes. 10.2. Giovanni?
Yeah.
Right here?
Yep.
Do you have a lesson plan too, or no?
No.
You never did a lesson plan? You don't have the answer for the questions here, right? You erased the board.
We know the answers, but
I don't think you're not supposed to have the answers.
we never wrote them there. No.
Right, erase the board. All right. Here we go. 10.2. And energy transfer. You can guys use the thing to click on it, right?
The marker is open. It's gonna dry out.
Yeah, can you please close it for me? Thank you.
Okay. Chapter 10.2. Thermal expansion and energy transfer.
Well, this chapter talks about that things tend to get bigger or larger when temperature increases, and it's the opposite. Also,
Oh, hold on.
when
Can you say that one more time?
it's right there. What she said. Are you making up?
No, you're
no,
fine.
no,
I
I
just
thought
wanted
we
you
were
to
saying
repeat what you said.
I thought. Okay, this chapter talks about physics and thermal expansion and contraction and
Okay.
the way thermal energy can be transferred.
Okay.
And like what I just said, things tend to get bigger and expand when temperature increases. How big?
How big?
A whole lot.
Well, they're gonna talk about that.
Really big. Really big. You can think about it yourself.
Okay. Vocabulary.
Guys, quiet.
Thermal expansion. Thermal expansion is when you have objects that increase in size, area, shape due to heat applied or temperature applied to it.
So, for example, like a hot air balloon, when it's in air, when you pull the string, this fire releases and it releases heat energy that caused the balloon to expand and which caused it to go high in the air.
Cool.
Conduction. Oh. Conduction is when heat, like let's say a kettle stove that's applied underneath. The warmth you feel on the handle is the conducted along the metal of the kettle.
Any questions so far? Yes, Elizabeth. Thermal expansion. Not like when you throw a balloon through it. Oh, it's not the same.
Did you ever hear? Like, anybody has ever gone up north for winter? To and everybody's ever stayed in a wood cabin? All right. So when it starts getting colder at night, right? You can actually hear the wood cracking, and it's a bit scary sometimes, right? But that's actually because literally the wood, as it gets colder, is getting smaller, right? The opposite happens in the morning when it starts warming up; it expands. In fact, this entire building, because we live in Florida, doesn't really see that much. But if we live it up north, the whole building could shrink by 2 inches. Like if we live it up north, right? And it seems like crazy, but it's true. It could do that. And if you think about it in terms of volume, that's a significant volume change, right? Now, that's why materials, when you're an engineer, you have to take this into consideration, especially since different materials expand at different rates. That depends on the linear coefficient of expansion. So if you build everything of different materials, which we do, we put concrete, we put metal, we put wood in the construction. But since those materials are expanding different, that could lead to structural problems. You know what I'm trying to say? Because say the beams expand at a rate that the concrete expands at a different rate. So that could make the bridge collapse if you don't take those things into consideration. So it's certainly very important for real life physics because you need to take that into consideration when you're building it. Even in a computer board, the materials you make it, as the computer gets warmer, the motherboard literally expands. But if materials in there have different thermal conductivities and different coefficients of expansion, you're literally going to affect the circuitry of the board. So that's why what you choose to put on the board, we use silicon and other things, majority of stuff is silicon based, but all the stuff that's in there matters. Does that make sense? And you have to take that into consideration. All right, keep going.
I'm gonna give.
Do you have another example?
Yeah,
sure.
Like I got a good example.
Okay.
I mean, let's say you have like a pot, like 10 feet, you know, and what happened is that as over time when you're heating up the pot, the handle started to feel hotter, why does that? Well, from a microscopic perspective, the particles start to vibrate and start to gain kinetic energy. So it start moving all over the place and cause collision through one particle to the other, and it do that along the handle. We cause the handle to become hot as well.
So it's basically collisions, right?
Yeah, collision.
Right? So conduction is literally
Yeah,
touching.
Momentum is in there too.
Any other
That's
questions?
part of momentum.
Any other questions?
Cool. You want one?
Oh. Insulator.
Okay. I'll go back. No, that's it.
Oh, okay.
Okay.
Insulators. Insulators are basically materials that are very poor I don't even want to say poor conductors, but very poor at conducting electricity. For example, things like paper, rubber, styrofoam, glass, and dry air.
So like, let's say we have like a wood rod, and you put it on a fire. The other end is gonna catch on fire, but on the other hand, it's not. It's gonna be comfortably cool, and that's, as Gio said, is a poor conductor of electricity, but also of thermal energy, which is why the whole wooden rod doesn't heat up.
Convection. Yeah. Convection. Imagine you have two systems, right? And say they're different temperatures. Each system will get each other hotter or colder.
So, like, it sounds confusing. It sounds kind of like conduction, but best example, a pot of water in the stove.
And you have another one
So
here.
like,
Okay, hold on. Just explain stuff.
so what happened is that there's the heat and there's like particles. What happened is that under when it gets heat up, it becomes less dense. So what happens is the particle moves up to the top.
Okay.
And the cool particle stays in the bottom. But also when the heat of the particle stays on top, it starts to cool down. So and the cool particle on the bottom starts to heat up. So it switches places and
Circle,
keep
circle
doing
around.
that cycle.
Okay. So this is an example, guys, of why it's so important to practice. He knows what he's talking about, but communicating that is another story. Understand? It's very important when you have a presentation that you need to practice. So can you go over it one more time? Because I know you know what you're talking about, but I want to understand what you're saying. No, you're close. Go one more time over that, please. Right?
So simply, it's just the one with that's less dense that has more heat
Okay. We'll rise up, right?
goes on top,
Okay.
and the one that's cool goes on the bottom. But it repeats that cycle because the one on the bottom gets heated up,
And then when the top gets cooled over.
cooled down.
Right. There's a really cool demo to show this that you could do, and I usually do it in my class. But ever seen a lava lamp?
Yeah.
It's based on that concept, right? Now, that's different from conduction because in conduction, things are touching to pass on the heat. In convection, whoever has the heat is moving. You see the difference? So conduction is me like touching him, he gets hot because obviously I'm hot, right? But convection is if I walk, my heat follows me. Does that make sense? So I used to teach physical science, earth-based science. I taught this to my younger kids. Like back in the day, Twilight was on, and I had a big crush on Taylor Lautner, and so I used to say that if Taylor Lautner walks into the room, right, and walks towards me, by convection, I start getting warmer. I'm saying, but even from far away, as I see him, are you with me? As I see him, that's radiation, right? The waves of heat coming from him, that's radiation. But as he walks towards me, it's convection, I'm getting warmer. If he actually touches me,
You get wet.
by conduction, I got much warmer, and then I actually expand. You know what I'm saying? All right. Okay.
I'd probably get
Woo! Just talking about it made me all You know.
So
Anyways,
so it was your man crush Monday. Alright, yeah.
continuing.
Yeah, so William just kind of said what I have here.
And the amazing part is that after all that, it still conserves thermal energy because it's just transferring heat. It's not losing. It's not losing anything. It has the same amount of heat.
Okay.
It's kind of like conservation of momentum too, in a way.
Because the particles have, if they're moving with that energy, the energy moves with them, and the momentum are going by collisions. The same thing. You know, can't miss that. Right? Cool. Next one.
Any questions? No? Okay. Radiation. Anyone know anything about radiation? No? Yes, Elizabeth.
Is that one due to the Japanese?
Too soon. Too soon. Okay. Radiation. I don't know how to come back from that one. Radiation is the transmission of energy through waves. Through waves, okay? Yeah.
Yeah.
Kind of like a person placed their cold hands over a warm fire.
Another example is like when you walk outside and you feel the warmth of the sun. Why does that? Well, that's because the thermal, like as the definition suggests, like the heat of the sun, the thermal energy, turns into like an electromagnetic wave that travels through space and onto Earth. So that's why you feel the heat of the sun. It's infrared waves coming from the sun.
Any other common examples of radiation? One less, violent?
I gave one that was pretty awesome.
Well, I mean, and common example is a microwave,
Oh, I like that.
Yeah, that uses radiation. Any questions? No?
Can I make a side comment? I mean, let me make sure when his presentation is over. Oh, test question.
Yeah.
Okay. I get two more after this?
Yeah.
All right. So these will be in their presentation, which will be posted online. You got it? Cool.
Yep.
Anything else?
We got a video.
All right, cool.
You got to copy it.
Sure. I'll try. This is why you have to send the lesson plan, because now how do I open that? Do you know how to search for this video?
Let's switch. No.
I'll search for it. What is it called?
Um,
How did you find it? Because I can't copy from it, apparently. Or either way, you're kind of out of time, so we have to go, unfortunately. Guys, he does have a video, but he's out of time to show it, all right? And you guys can click on it when you open the presentation.
yeah, I'll send it to you again.
All right. Okay, man, very important for you guys to send the lesson plan to me also so these things don't happen. All right, I already saved their video. It's going to be on the presentation. It's going to be along with everything else. Okay, so I can't. They didn't really have a demo for us, right? All right, 10.3. Yes.
Oh, my bad.
Yes. Ahí te empaté.
Don't post our PowerPoint because we have these answers.
No, so you just send me one
Yeah,
without
we'll fix that for you.
it. That's fine.
Try to do the demo. I mean, technically, it's in my phone, and what I was trying to do was cut it, but the video was too long.
I understand. I just have to grade you what happened.
Okay, do you want me to show it to you?
We'll talk about it later, all right? Because we gotta keep
I
going.
wasn't really that. I'm not really experienced.
It's fine. Don't worry about it, man. All right. All right. Now, take good notes, people. Notes count towards your grade as well. All right, Jennifer and Orlando. Let's make sure I get your stuff. Hold on. Yeah.
Wait, ready?
When you can't do the demo here, have a video of a demo. All right? That fulfills two criteria. You have the multimedia thing and a demo. That's what you have to plan ahead.
Is it okay if it's not us doing the demo?
It should be you guys doing the demo. Yes. We talked about that. All right. So let me make sure I save this thing. You just learned that? Wow. It's okay, man. Real life struggles. Where did it go? I'm just making sure that their presentation is saved there. Already burned in the right place. Okay, perfect. Okay, now find yours. Okay, lesson plan.
I have everything in the lesson plan. I just only in the presentation. I only put like the talking points.
That's fine. That's fine. I know.
Wait, let me look through it because like I had to add certain lesson notes. So
Are you good? All right. Okay. Just click on things. There's a button on the top that says Open Presentation that's going to load in a second. Oh, he can. It says Start Slideshow somewhere in there.
why is it so small? What?
No, when he starts it, it's going to become bigger.
I did it in my
Hold on. We have to. Do it.
Where does this go?
There's a little bag for them in there. I think it's on the other side of the room because we use it for weights and
What
things.
is this called?
It's on that side. You see them. All right, now it should work.
Yes.
All right, good.
What the heck?
Don't worry about it.
Okay.
Just say what it says.
All right.
Shh. All right.
Okay. So. Okay, so this was prettier when I did it at home. I don't know what happened to it, but I'm just gonna. Okay, so 10.3 capacity. Okay, so James Joule did an experiment to because heat is another form of energy and it's not lost or it's part of the conservation of energy. So James Joule did an experiment to test this. What he did, he used this device that had two masses attached to it. So then the masses would drop. And the work done by gravity when those masses dropped caused the paddles inside of it to spin. When the paddles moved, it caused heat inside. It caused the water to raise temperature. By measuring the work done and the temperature of the water, the temperature change in the water, he was able to prove that the energy was conserved and it was just turning into heat.
That's pretty cool. So like you lose potential, gain kinetic, and also heat. All the energy is accounted for. Very nice. Okay.
Okay, so the units of heat, 1 calorie is 4.186 joules, and 1 kilocalorie is 4,186 joules. Okay, what symbol Q in equations?
One second before you guys continue. Make sure you go over the objectives of your presentation before you start your presentation. Okay, guys? So they're trying to explain what heat is and its units. They're trying to relate work to heat, right? Which we're going to say that, and they're going to use practice with formulas, and they're defining and what specific heat is all about, right? And then they're also talking about the calorimeter and how that works. So that's like a whole class. But let's see what they can do in 10 minutes. All right.
So Q represents heat, and when heat is added to a system, when thermal energy is added to a system, heat is positive, and when thermal energy is taken away from a system, heat is negative, since heat is a transfer of thermal energy. So that makes sense. Okay, this is a practice problem that's using work and heat. So it says a 74.0 kilogram person drinks a thick, rich, 305 calorie milkshake. How many stairs must this person climb to work off the shake? Okay, so each little height of each stair is 20 centimeters. So the total height that he's going to have to go is h. So we'll represent that by h. So you would relate heat to the work formula. And the work here is being done by gravity since you're going up the stairs. So it would be Q equals mgh. So then you would just solve for that and you would plug in the numbers. So it would be, you have 20.0 centimeters for the small height, you have 74.0 kilograms for the mass, and you have 305 calories for the heat. Now you would convert the 305 calories, because calories with the capital C is used in foods and stuff, is actually, I believe, 1,000 normal calories.
It's a kilocalorie.
Uh-huh. It's exactly.
But since that standard SI unit is joules, you still have to convert that to joules.
Exactly. So you convert that to joules, and what's it called? And then so you just plug it into the equation, Q divided by
Holy
M.
crap, that's really high.
And then yeah, it's extremely high. It's
So,
8,800.
It's almost 2,000 meters.
Yeah, I read. It says it says that this is enough energy to go all the stairs up in the Empire State Building, all the way to the top. For one milkshake.
Although, of course, you got to remember that a majority of the energy that you consume goes. This is a little bit of biology, but I can't hold myself. The majority of the energy that you consume goes towards heating yourself up, like literally keeping your body warm. So a lot of the burning of the energy, just sitting there, doing nothing, you're going to spend a lot of energy. Now, if you have a job that you're standing up all day, or moving around a lot, or if you work out a lot, then that could become not true, But in general, most people, the largest percentage of their energy. I'll give you an example. Right? My basic metabolic rate, right, is about 1,400 calories, based on my lifestyle, age, weight, size, and stuff like that. So that means if I do absolutely nothing, right, and I just lay on a bed just to keep my body temperature and keep me alive, it takes 1,400 calories a day, right? Which means if I eat less than 400 calories, I have to start This is Mr. Gary Archbold. He got into Stanford. I want to congratulate him for that. What's up? Which one? For the test thingy? Oh yeah, okay, good. All right, just come here. I'll give it to you in a second. All right, guys. So what was I saying? So now, because I actually keep track of that, it takes a lot more calories than that to my actual life. Like yesterday was 4,200 calories, right? That's a lot. So that's why you have to eat a lot, to if you work out a lot and if you have a very active day. I'm on my feet all day, and that matters. You know what I'm saying? Imagine someone that works on agriculture, or someone that works on a hard, labor-intensive job. That's why you eat a lot, because they spend a lot, right? It's very interesting though. That's pretty crazy.
Yeah.
If you're trying to burn off the milkshake, Stairmaster, you have to do 100 floors. Have you ever done a Stairmaster before? Remember that next time you drink a milkshake. Coke is even worse. All right, good job. All right, your time is back up.
Can we go back?
I'll go back.
Okay, so specific heat capacity. For different substances, it takes more or less thermal energy for the substance to change temperature 1 degree Celsius. An analogy you could sort of use for this is think of two vases of the same height but different widths. The bigger vase, or the vase with the bigger width, is going to require more water to fill to the same level as the other one. So you can think about that with thermal energy. Some substances need more thermal energy to change temperature than others. Water has a really high specific heat, which is what allows for our moderate climate in the world. Because not, the water would be heating really quickly. Yeah.
No, the opposite, actually. Water, you said moderate climate in the world. Like when water heats up, right, the oceans actually become cooler because it takes a long time for the oceans to absorb that much heat. Does that make sense? It takes a while for the oceans to heat up because they're water. So because water has such a high specific heat, let's just say, the ocean water actually helps the world not stay as warm as it should. Are you with me? Once the water actually evaporates, though, it takes that heat with it, and it stays in the atmosphere like a greenhouse gas that you should definitely learn this. That actually warms us at night. So the water vapor in the air is actually what keeps our temperature moderate, especially if you think about nighttime. During the nighttime, there is no heat influx in this side of the world, right? Where it's night. So So the only thing keeping you warm is the heat of the atmosphere. And primarily, it's carbon dioxide and water vapor and methane gas that actually does that job. So if you take away water vapor from the air, you live like in a desert, right? At night it drops tremendously the temperature, and it actually gets cold, right? If you combine that with the fact that in the desert there's less methane and carbon dioxide because there's less life forms, that's why desert climate is so varies temperature so much. Does that make sense? Meanwhile, places which are warm like Florida, you go out at night, it's 80 degrees because it's 90% humidity. Even now in the winter, by the way, this is really bizarre, but the humidity yesterday was like 70%. Yeah. That's like really bizarre because at the winter, you're not supposed to have that kind of humidity. Right? It's supposed to drop to the 40s, which is still high here in Florida, 40% humidity. You know? But what does that mean, 40%? It means that 40% of the water that can fit in the air is in the air. You know what I'm saying? So that's really, really humid. When you get to like 100%, it basically becomes fog, right? Or rain at that point. So that's interesting. Florida is always so close to that it's very easy for it to rain in Florida. And that means the clouds in Florida are also very low because you don't have to go very high to get to the dew point. So the formation of clouds in Florida are very low, you know, because it's so wet. Does that all make sense to you guys? So, and also because we are made of water, it also helps us maintain balance. Does that make sense? So all these things are important for life. And it's also the thing that we use in calorimeters, we're going to talk about. Water is a good measurement to figure out how much things are going up. Thank you. Right? Good work. All right?
That's really small. I don't think you guys can see it. Specific heat also has a formula, which is specific heat.
See.
I don't know. I want to write that.
Oh, you like that? Oh, the dryer actually did dry, didn't it?
Yeah.
Here, try that one. Toss that one out.
And that's why I play baseball. Good.
Oh, see, I go to someone?
Ken.
It equals heat over mass times temperature. That's
So how much heat it takes for a gram of mass to change by a certain temperature?
which in short terms is C equals, or the C equals specific heat capacity, Q heat over M times delta. That's the formula for specific heat capacity.
So also, if you think about it, if you solve for Q, then you can figure out how much heat you would need to heat something with a certain C by a certain temperature or in a certain amount of mass of it. So, so if you knew like how much mass of water you have and what the heat capacity of water is, and by how much you want to change the temperature, there you go. That's this.
So
I'm just gonna shut up here.
I have a practice problem.
Yeah.
Which is, it asks you, what is the temperature change of 1 kilogram of water if there's 505 joules of thermal energy added to it? So you write down the given. So the
404,186, right?
that's the heat capacity of water.
By the way, that's what's defined as a calorie. Okay.
Yeah, 1 calorie, 1
Kilocalorie. Right?
kilocalorie.
Yeah.
And then to find for the Q, you have to rearrange the equation, and then you move this to the other side.
Oh, for the end. Good stuff.
And then
Yeah, you're solving for T, not for Q this time.
yeah. So you got the 505. 1 kilogram. And then the other 2. And then you have to multiply the 1 with the same thing, and then you divide the capacity.
4186.
4186, 505, and then it gives you that.
So it doesn't change by much, you see, with that much energy. Now, anybody remember doing the work lab and all that actual work that we did? We generated like maybe 5,000 joules, all right? Or actually, I think it was 50,000 joules or something like that. Anybody remember? So what was it? In the 40,000s, right? So if we're talking about that number can fit there 80 times. Even then, you only brought water up by 8 degrees. Imagine that. You've done all that work, and yet water barely heated up. Right? Because it has specific heat.
And then this is the
I don't know. Calorimeter?
calorimeter. So the
that good?
calorimeter cup is just, it's almost like what Lombardo explained in his he explained in 10.1. So you get an object that's heated up more than water, and then the water is cold, you put it inside the water, and then they go to the thermal equilibrium, and then they're the same temperature, which the energy is conserved and no thermal energy or no energy is lost. Like so. Yeah.
So then we have like a demo of this movie that Calorimeter.
Right here?
Yeah. It like has no audio. I don't know.
Was that the last thing, or is there something else?
Yeah.
That's it.
Do you have your questions up here?
I have it in my Word.
Make sure, can you send me a new presentation that has your questions in it so that I can share with people? Because otherwise they can't get the points from your thing, right? And you can't get the points for grading, right? Okay. By the way, doing the questions is not mandatory, okay? So you don't have to do it. But if you do it, you get points, right? For each question that you answer. And then people who grade it also get points. As many sets of questions as you want, right?
Okay.
Supposed to be sound to this?
No. I don't
Okay.
know why. It's the best video I found.
Okay.
Okay. So they're using the cups as a calorimeter. So then he's setting the weight so that's 0. So it doesn't happen. So in the water, 100 milliliters of deionized water. We're recording the mass of the water.
That's not 100 milliliters for sure. If it was deionized water, it should be 100 grams, right? So that's weird. Someone measured wrong.
Do the beaker thing again where you set the weight. 0. They're adding a different substance to find a specific substance. I don't know the
Some sort of thing.
Copper.
Okay, good.
50 grams of copper to the test tube, and then they just record the mass. Okay, so they're heating the metal, but you can't allow the water meter to get below the level of the metal in the vacuum. Okay. So, they're heating it to a higher heat than the water in order for the experiment to work. Again, let's remove the drop water again. It's not important. They transferred it to the calorimeter.
Now, since you know the specific heat of water, whatever heat whatever heat the metal is losing, the water is gaining. So you can set the equations equal to each other because Q will be the same. Does that make sense? The Q the water gains is the Q the other one loses. So you put Cm delta T equals Cm delta T, except one C is from one and the other C is from the other. Like you literally do that. It's a classic experiment. Like you do that. Cm delta T, and this would be the water, right? Copper, delta T of copper. Right? And so you set them equal to each other. If you know the mass of copper, the mass of water, the centigrade of water, you can solve for the specific heat of the copper. It's a very easy experiment. You can do it here, by the way, if you ever want to, for curiosity. Right? All you use is styrofoam cup in a hot plate. All right? So if you ever want to. My physics 2 students did this year.
Hi, my name is Elise. We're going to talk about the experiment on...
All right, very good, guys. Thank you very much. This is how you do it. All right? The only advice I would give to you guys is practice your speech more so you can have more fluidity when you're talking. So this is, all right? So, because being a teacher is also, I mean, I'm not saying you work, but it's also not being boring. And when you're too slow and methodic, then people start snoozing. You know what I'm saying? And I didn't say it was boring. I'm saying you're borderline, almost got there. Yes. All right. Other than that, it was really good. Okay, so everybody, the next one should be 10.4. Who's got 10.4? All right, let's do it. Gotta get at least to 11.1 today. Okay, you have. Where's yours here? This it?
We like to set it on top.
This it? Right here?
No, Anna sent it to me.
Like right now?
Yeah, because we have to.
I don't think I have it. Like, just send them like right now?
Like at the beginning of class.
Oh, okay.
Right
So I should. Not this? Something else? This is the lesson plan.
The report is in the lesson plan.
I got you. Talk about, do you have something to show or are you just going to talk?
We have a present.
Oh, okay. You see it? Right here? Okay, cool. Nah, you're good, girl. Don't worry about it. This is a cool group. They're nice. Don't worry about it. Everybody's in single. All right, let's go. Shh. They have an awesome. I love Prezzies. They're great. You can use the clicker, okay?
Literally, I use Prezi like information for the entire ABC project. You could copy and paste it as well.
Okay. Wait, the presentation hasn't started yet. Is that supposed to happen? I think this is like a link to, can you want to log into your Prezi, please? Makes more sense. Go. You in capitals, so when you get the password, make sure you take the caps off.
Oh, wait.
That's fine, this won't matter, but when you get the password, it won't matter. Okay, so take the caps off. All right, okay. This one? That link you sent is a link to watch the present. So you can be presenting it right now, and people will be able to watch it. This is present remotely, so you can be sitting from there and clicking on it, and somebody somewhere else could be watching your presentation. That's kind of how that works. It's a cool thing Prezi added lately. Right. Guys, quiet down. Here we go. Shh. Here are the points going off because you're talking over people.
So we're going to be doing section 10.4, and it's phase changes and latent heat, and Ana Gutierrez in this is So the reason why we chose this is because an hourglass kind of gives you a sense of equilibrium. So we thought that we would put the bubbles kind of in equilibrium with each other. basically solid, liquid, and gas. So phase equilibrium is when a system is in phase equilibrium between a liquid and gas phase, liquid and gas phases, the particles leaving the liquid and returning to the liquid must be equal to each other. Alright, so keeping this picture in mind, this is a closed cylinder. Okay, and this is in liquid form, then it's turning into gas form, and this is equilibrium. Alright, so that is okay. Right. Great. Yes, pressure. So pressure is the force applied to a certain area. Alright? And the equation. Okay, so the equation for pressure is P is equal to
Sorry. I got English, I'm sorry. Stupid whiteout.
okay, so alright, so pressure is force divided by the area. So pressure is directly related to force and inversely related to area. And you can write it another way, so it's easier. P equals MA over the big A, which is area. Okay. And the SI unit for pressure is Pascal. So the SI unit
Did you guys do one of these?
is newtons per meter squared, or a Pascal. Okay? And we can rewrite the Pascal as 1 kilo Pascal, which is equal to 10 to the third Pascal. This is the most common way of using it.
I like the grunt.
Oh my god.
You want to click here?
Yes.
Okay.
Okay, so going back to the example, to the picture that we showed on the first slide with the 3 containers, if you would increase the temperature of that container, the particles in the liquid would increase. So if you want to have an equilibrium between both the particles in the liquid and the particles in the gas, you have to increase the pressure of the gas. And that is what equilibrium vapor pressure is the pressure of the gas in equilibrium with the liquid. Alright?
So see, when the air is too full of water, for example, no more water can go to the air, right? And that's like the whole premise of a pressure cooker, right? Because that you can keep raising the temperature and make it hotter, but without losing the water anymore. Does that make sense? Right? So because no matter how much you heat it, when this is already at the maximum vapor pressure, it would be in equilibrium with the liquid and it cannot evaporate anymore. So you can cook it in water at a hotter temperature inside of a pressure cooker, if it makes any sense. Right? We're going here? Boiling point?
Yes.
What happens?
What does this stand for again?
Yeah. Okay, so the boiling point is basically the temperature a substance has to have in order for the external pressure to equal the vapor pressure. So when you heat something up and it gains enough pressure, it boils. And evaporation is a substance changing from a liquid phase to a gas phase. Now, so basically, like, for example, when you sweat, like, when sweat glands, like, get on your body, like, when they heat up, they gain, the particles in the sweat glands gain kinetic energy. And then that causes them to evaporate. And it causes for thermal energy in your body to extend outward into the atmosphere. So that's why it helps you cool down when you sweat too, because the sweat evaporates and it releases your thermal energy.
Now the biggest difference here is that for boiling, the entire liquid is doing that almost at once, right? Everybody is at that temperature. Now evaporation is just one molecule at a time reaching that kinetic enough kinetic energy to escape. You know, either one won't happen though if the air pressure or the vapor pressure is too high. Does that make sense? So if you add pressure, what happens to the boiling point? You need to increase it. You know what I'm saying? So that's why if you go out to the Empire State Building or to the Mount Everest, you know, even more, it actually takes less heat to cook something because, you know, the pressure, vapor pressure is lower. Exactly. Very good. Very nice case. Right. Here?
The next one
You gonna go here? Okay. Ooh. Very important.
latent heat. No, that wasn't next one. Next one was atmosphere.
Is it here?
There we go.
Okay.
Evaporation.
Okay.
So, little more, but basically it's possible for the atmosphere to evaporate itself, like the actual gas in the atmosphere. But it needs to try harder to overcome gravity. And the thing that happens is that it needs to, like, the kinetic energy needs to build up enough to be like I have the number here, 11,200 meters per second, which is like rocket speed, in order for it to actually leave the Earth's atmosphere and like expand. So yeah, that's in order to atmosphere to evaporate, it must overcome gravity.
Now remember how I said that water traps heat, right? So more more heat means warmer atmosphere. But warmer atmosphere means more evaporation, which means more heat, more atmosphere. See? So it's a feedback loop. Now since carbon dioxide also traps heat, it feeds into this even more. Are you with me? But it gets even worse. The oceans trap carbon dioxide, a lot of it. So that as water evaporates and you have less water in the oceans, does that make sense? Then even more less carbon dioxide is trapped. And then it gets even worse because then the ice starts to melt. And as the ice starts to melt, you get a situation of the ocean going up again, so you have more volume. But now with the ice melted, the permafrost gets exposed and the methane gas is trapped underneath it, gets released. Methane is a greenhouse gas. Feeds more into the feedback loop. And that's how you get into a runaway effect that warms up a lot. Whether that's caused by an influx of carbon dioxide that's extraneous from a human action, we're not sure of. There could be a million other things. The world could be warming up because of a natural geological process, a natural greater increase in solar output, or changes in the Earth's orbit. There is no evidence to suggest that any of those precession or geological processes are increasing at this point. So most likely it's human made, although we can't definitively say it is. But I always like to plug that in when it comes up. Very good, guys. One more. This will be the last one today, by the way. So are we going over here? Here. Okay. Okay. All right, good.
Okay, so latent heat is the thermal energy required for a substance to change its phase. So to change from a liquid or a solid or a gas. So basically what happens with latent heat is that, let's say you have like a cup filled with ice and you have it in a hot plate or something. You put a thermometer in it. It will be 0 degrees Celsius because that's the freezing point of water, as we learned from 10.1. That's the freezing point of water, is 0 degrees Celsius. It will not change until all the ice has melted. Like it's still heating up, you see the ice melting, but it will still be 0 degrees until it's a complete liquid. And then it will remain at 100 degrees Celsius, which is like the boiling point of water, until it completely forms into a gas. So that time interval between the phases, it's what is latent heat.
This is really interesting. So as you warm something up, and so it's easier to see this in a liquid to gas, right? She said this one, but it's also easy to see here. So if you warm up a liquid, it will go up, hotter, 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 hotter. But when it gets to evaporation point they talked about, the boiling point, it no longer warms up. It just stays at that boiling point until the entire liquid is gone, right? You can think of it as that any extra heat you added is not going to warm it up. It's going to make the thing what? Evaporate. Does that make sense? So that's kind of how that is. So if you're trying to figure out how much energy it takes to go from here to here, you're going to calculate that plus this latent heat, that plus this latent heat, plus that. And this is something that we do in physics too, you know?
And there is a formula for it, and it's Q equals ml, where this equals mass, this equals latent heat, and this equals the heat, the actual heat, and just basically like the greater the mass, the greater the actual thing.
And here are their test questions, right?
Oh, there's a video.
That's a video you want to show?
It's
But to show you, that's just showing where they are. It's in the corner of the Prezi, so make sure you check that out when you see the Prezi.
it's in the
It's in here? Oh my God. Have to click here? It's like
There's more over
Inception.
there.
It's like Inception. Oh my gosh.
No, but it's not. No, the video first.
The video first, okay, fine.
Change of state and specific latent heat. Specific latent heat is the amount of heat energy required to change the state of a unit mass of a substance without change in temperature. The word latent means dormant or concealed. Let's perform an activity to find out why the heat energy required to bring about a change of state is called latent heat. Take some ice cubes in a beaker. Suspend a thermometer into the ice cubes and note its temperature. The temperature is 0 degrees centigrade. Heat the ice cubes. Record the temperature after every minute. Keep stirring the ice-water mixture constantly so that the temperature is uniform throughout. We observe that the thermometer reading remains constant at 0 degrees centigrade, though heat is being constantly supplied. The temperature remains constant till the ice completely melts to water at 0 degrees centigrade. Continue heating water which is at 0 degrees centigrade. We observe that the temperature is increasing. Record the rise in temperature till the water starts boiling. Continue heating. The boiling water gets converted to steam.
Because the class is going to end. And what is this about?
The conditions.
Okay, guys, I just want to say something important. Hey, listen. So next class, we're going to hurry up a little bit more because we have to do 7 of them. We have time, but we just can't waste time. Okay? Now, one more thing. Notes that you took today must be turned in today to get credit for them. Right now, on your way out. Alright? You don't have to have notes on your own presentation, but other than that, you have to have notes. Alright? Has to be sent to me right now. Alright? See you guys next class. Don't forget, notes taken at home on the chapter are due next class.